Thank you everyone so much for coming. This is our July webinar for the Materials Decarbonization and Sustainability Center at UC Davis. And today we are joined by one of our faculty affiliates, Dr. Somaya Nasiri, who will be speaking in particular about her work with the Lab2Slab program. So she is an associate professor at UC Davis, and she is also a principal investigator with the UC Pavement Research Center. And she has a great presentation prepared for us today. We do ask that you save all your questions for the end. And after she's given the presentation, she'll go through them. And there is a Q&A box. Should be at the bottom of your screen. So you can add your questions as soon as they come to you so you don't forget them. And at the end, we'll pull that box up and go through them and also open the floor to any further questions. So thank you so much, everyone, for being here. And thank you, Dr. Nasiri, for speaking with us today.
Thank you, Kelsey. It is a pleasure to be here. And like I said, very excited to see so many of friends. Which screen do you see, Kelsey?
I see, there you go. There it's
Okay.
full. Yes.
Is everything good? Thumbs up? Okay. Well, thank you so much for everyone for being here. I should acknowledge my great collaborators, Professor John Harvey and Sabby Miller, who we work closely on this. And I'm here to speak a little bit about a framework, an evaluation framework that we set forth for kind of managing risk and getting materials through, new materials through, or new technology through. It kind of applies to any sector, I want to say, but our focus is primarily today on concrete. And let's jump into it, talking about challenges. What is the challenge that we're trying to address today? And thinking about challenges of the concrete industry and the construction industry, and then making it a little bigger, the civil engineering in general, the status quo and the way we do things on a daily basis can become so entrenched that we could become problem blind. And I did not come up with that terminology. I have the resource down below. It's a really good book that I've been reading, and I highly encourage it. But basically, the idea is that we can improve our processes, we can improve our material, increase the durability of concrete, we can improve our efficiency, the way we make concrete, the way we place concrete. We can optimize the material itself. We can do so many things differently than we do on a daily basis. But all of that are associated with some risk because we'll have to apply some changes and we may be outside the standard practice. There's a good example in the book that I just mentioned a second ago. And this was about open heart surgery and how surgeons will do open heart surgery to remove, to address clogged arteries, and until angioplasty came about. And what was interesting to me is that the best of the surgeons that were the best at doing open heart surgery spent quite a bit of their career fighting or imposing the new method. So it just kind of shows that even the best of us, and especially the best of us, would be risk averse because this is a change and the risk can fall on the individuals or on the leadership, on the management, or on the firms, and someone has to take the risk. So the idea here is that let's come up with a framework that we can identify the risk and we can come up with a way to manage it, a framework to manage it and to address it. And then ideally, the goal would be to adopt change not within decades, but more within 2 or 5 years, and be open to a culture of change. And so as we've been exploring this idea and we've been, facing these questions from a broad range of a stakeholder, from the producers, from the contractors, and from the state DOTs, why doesn't the change happen already? Why does it take so long? We kind of looked at what is available there in social sciences, what do psychologists say, what kind of models are out there. And I have found a few of those behavioral change models that are applicable to the concrete industry and the construction industry, but they've generally been used for tech, for business, public health, a variety of sectors, but generally within the tech industry, they're very common, but we can learn some aspects from their principles. and help us build that risk management framework. So the first model that I want to introduce to you, and a lot of you may have already seen this, is called the Diffusion of Innovation model. And so this model breaks down the entire population, as you can see on the screen, into fragments of population. And describes how various fragments of population will take on to a change. So what you can see, that tiny 2.5%, those are the early on adopters who we want to engage first. And those are for us to translate back to the concrete sector. Those are maybe the firms that are willing to take the risk or have the resources or the culture already that can take on big projects and absorb the failure if there is any. And I would give an example for maybe the owner of Burj Khalifa or whoever set out to build the tallest skyscraper in the world and take on that risk. After that 2.5%, we want to engage the larger early adopters. And then what you see on the screen, then there is that chasm. There is that gap that technology or the new material or any innovation has to cross, has to bridge to be able to then make it to a larger population, 34%. And then as I've been presenting this, and I see my friend Mike Smith here from CEMEX also, we've been identifying a second chasm. So we would have a modification to the authors of this model, developers of this model, to introduce one more yet chasm there that the technology will have to bridge and to cross to make it the late majority. And now the technology's made it through the majority of the population. I was presenting this framework to another group, and somebody brought up a really good point that they've been working with the school district, and they are unwilling to take on cold fly ash in their concrete mixes. And so it reminded me that there is always that small portion, 16% of the population, that just would not take on to that change. And that is okay. And that is okay. That's just the cross section of the population. So the next model that I thought was found it quite relevant to how we perceive change, or how what are the barriers that we see, or what are the different steps for why or why not an agency may adopt that change, that particular technology. This model, UTAUT, and you can see the reference at the bottom if you want to read more about it, but it's summarized it in this flowchart. Let's start at the top. The first item is how, for a user, the user standpoint, or a firm, or a DOT agency, how would this impact my job? Is this going to be a failure on my record? Is this going to damage my reputation, or even worse, am I going to lose my license for this? Or am I going to, my firm is going to see some financial losses, lawsuits, and things like that. And then the second level is effort expectancy. In this, for us in the concrete industry, again, it can translate to, okay, this material, how easy is it, or how difficult is it to take it on? Is it compatible with the admixtures that I already have on hand? Does it follow? Do I need extra silo? Do I need to make changes to my regular mixing batching? That would be an example. And then also, you know, what makes it a lot easier for material to be taken on if there is already a path to standardization or to be accepted as approved material list. If the path is there already, and you know what test needs to be done, then that effort expectancy goes down drastically. And then the other two I kind of group together is a social influence. So for a public agency, maybe you would be like, oh, what other DOTs are doing it? Are they doing it, or they're not doing it? Or is FHWA doing it? You know, who's the leader in the industry that is maybe trying out this new technology? So maybe it goes back to that 2.6% early adopters, or some of the larger early adopters, and kind of following that lead. That would be the social influence. And then finally, at the end, facilitating conditions. And I translated that as policies, governmental or agencies that set policies like net zero goals that we had, some of the procurement policies that were coming out, tax credits, grants, and funding opportunities. So all of these coming together, I thought that model was a really good representation of some of the barriers and some of the things that may slow that change. Another model that I thought was interesting was kind of addressing the question within larger firms and even public agencies, those who are in charge of our public infrastructure, right, like DOTs or federal highways or things like that. How could they embrace change? And And a lot of that comes down from a top-down approach of setting expectations and working on applying that culture of change. And so this Kotter's eight-step change model, and you can read more about all the steps, and it comes with a lot of details, but I kind of grouped it into three major groups. And the first the steps could include, these are my interpretation of the model. It could include for a large firm or an agency to form committees and appoint leaders to the committees and follow on with the committees and follow up with the committees and check on their progress, and then give them resources so they can manage their risks and give them awards and celebrate their successes. In the middle core area is to, again, give them the resources so they can scale up the technology and they can continue to experiment, they do trials, do test the slabs, do demonstration projects, and then kind of normalize that experimentation and failures and remove the fear and the stigma and that negative reputation that may come out with, hey, we tried it out and it didn't work. Let's get that out there and let's talk about why it didn't work and not be afraid of it, not be afraid of failure, and create feedback loops so we can continually, a product that has been tested, we can continually update specs and continually get better and better at it. And then finally, make that a culture across that institution. Promote innovation, award those that embrace innovation, and provide training and continuing outreach to the entire agency that we are open to change and we want to continue to get better and improve our practices. So those are some of the culturally and behaviorally barriers and steps that are involved with taking on some change and improving the way that we do things on a regular basis. Now let's talk about, for that innovation or for a technology or a new material to be able to make it all the way to a standard practice, for all of that risk to be addressed, it has to go through a process. And that process involves research and development somewhere over here, and then getting it all the way to commercialization and standard practice. And so what research shows is that somewhere in the middle, all the resources get challenging and sparse, and they call that the valley of death. And that's essentially, it's trying to say that is where good ideas could go and stall, ideas can go die. And so I looked on the internet, I was looking for that chasm, I was looking for a valley, a photo of a valley, and I thought I would go with something really intense like this, where you can fall in and the idea can die there, crash in there, and the clashing waters, right? The idea here is that a technology would start, and this comes from NASA's technology readiness level, TRL, would advance all the way from 1 early stage all the way from 9, which is deployment and commercialization and standard practice, right? So what we're looking for really here is a bridge. We're looking for the bridge to be able to help support development and provide evaluation, validation, feedback, and performance validation, because there are challenges here in the middle that need to be bridged, and those could be funding, scaling up, getting permits, and getting over that chasm to make it all the way to here. So that brings me, that background all the way, brings me to this framework that we want to talk about today, and we refer to it as Lab2Slab2Practice. And this framework is designed to kind of help overcome the two valley of death that we've been talking about, the two large valleys to overcome. And the way we have framed it is really focused right now evaluating supplementary cementitious materials. This has been a work that has been supported by Caltrans. And we've been focused on finding alternative supplementary cementitious materials to coal fly ash and the slag. But it's a framework that can be applied to any new materials that come into that wants to make it to the sector, or any new technology. So considering evaluation of SCM or supplementary cementitious materials, we start off by basic characterization. And this is, your mineral phases, your oxide composition, particle size, thermal activation, if anything needed, XRD, XRF, getting all of the pozzolanic reactivity, and then doing cube testing, and then everything checks out, then advance to a larger scale. So you can watch my hand. It's literally, we're going from having, a few grams of the material, going to maybe 1 kg of the material, and then we're going up to maybe having a bucket of the material. So we're scaling up. And then early on, we want to check environmental claims, and we want to just use this as a screening tool and weed out the ones that the claims don't make sense, check out cost, check out scalability, check out whether we can have a supply chain established for this new material. Does everything check out? If everything checks out in this early investigation, then we want to move things forward. And what we do at this scale, then we call it the slab scale. But this is where the quantities for the producer, for the innovator, we're going now from a bucket of the material, we're going to a super sack of the material. So at this stage, they should be working on producing larger amounts in tons of the material, so we can place at least, a few slabs, a few tested slabs of it, look really at constructability of the material. And then we'd like to be able to do this in various climates with various aggregates and see how it performs. So by doing this, we're communicating, and I'll show you through reports, open houses, communication, helping that innovator bridge that valley of death and make it all the way to a larger scale, where at this point they're scaled up and they're producing tons of the material. And now we want the highway agencies, the cities, the counties, universities, and all the industry that use a lot of flat work, a lot of pavement, for example, or a lot of buildings, to be able to put pilots of this and use it on their projects, and continue to communicate the results and the performance and constructability, produce environmental product declaration at this point, and get federal support to continue to bridge that valley, which is going from those pilot projects all the way to becoming now a standard practice where, they do put that material in concrete. That's a standard practice. That's how we do things, right? So at this point, then things have made it to the agency specifications. It has its own standardized spec, ASTM, AASHTO, or what have you. And also training the workforce becomes a really, really important part of this. Okay, so I presented the framework in a theoretical manner so far, and I'd like to give you some examples as we go through this, and I'll come back to, maybe I'll touch on a few programs that have also implemented those. So we're going to go through an example implementation of this framework. So I'm gonna use natural puzzolans as an example. And this, I don't know how many of you are familiar with puzzolans, but these go back to ancient times, to Roman times, in fact. And, the time they used to make concrete or concrete-like substances with volcanic tuff. And they call it pozzolana, and that's where the whole story began. And we still have standing structures from that time that have withstood the test of time and have proven durability. But coming to modern construction, we've also used pozzolans across California. This is where we've had pumice deposits, and it was discovered by back then, today we call them Caltrans, but back then the highway agency employee Stanton, who demonstrated for the first time that they can actually, pozzolans in California can mitigate alkali silica reaction. And they're a very good additive for concrete. And we have a lot of public heavy civil infrastructure like dams in California and the western area of the country that have pozzolans and a lot of pumicide type materials in them. So now we want to go back and see, look, we're low on coal fly ash, we're low on slag, potentially, right? Until we want to diversify. We want to have various types of additives, supplementary cementitious materials to use in concrete. So if we go through that framework that we talked about, and the first step, if you remember, was the characterization at the laboratory scale, and we needing a few grams of the material. So, as it is with the binder portion of the concrete, we need that surface area. So a lot of it comes down to activation, and that whether being mechanical activation, thermal activation, but that has to be done, and the characterization has to be done in terms of the mineral phases, in terms of the surface area, fineness, all of those. And then what we put a lot of focus on is the pozzolanic or latent hydraulic reactivity of the material. And these are tests that can be done on very very, very small amount of the material, yet give us a significant amount of information to just screen a very early on screen these materials. We can do small scale cube testing to look at strength, but also look at water demand, which is very important aspect of these additives. We can look at their alkali silica reactivity also, in a small presence. So we're looking at early on. So as I go through the presentation, I cherry picked one of the first materials that we put through this whole full feedback cycle. And this material was produced for a pure base. They produce metakaolin mixed with a silica type SCM. It is produced locally here in California, in Ione, California. And everything is started, like I said, with the characterization of the essential oxides, looking at density, moisture content, any carbon or organic matter, particle size, everything checked out. So we did the first level of screening, looking at alkalis and all of that, and progressed to looking at the results of pozzolanic reactivity. So what we really like to look at in this graph, we place a little bit of the material in an alkaline solution and look and see how much heat is released in isothermal calorimetry over 7 days, and that's what you see on the y-axis. And then we also take that paste out after 7 days, and we measure how much calcium hydroxide is consumed in that sample by thermogravimetric analysis. We plot the two together. We've tested so many materials at this point that we've come up with boundaries and boxes for how to label the material. We've also checked that with some of the work available in the literature, and the boxes kind of match up. So you can see that pure-based material that we're using as an example today falls in this middle area, which we like the material to fall in, pozzolanic. What we call them less reactive versus this area is where we get a lot of heat, and those are the super uber reactive materials. We're not necessarily looking for overachievers. We're looking generally for materials to be in this area. And then some of the other materials may be latent hydraulic, which fall in these other boxes. This box down here is our reference for an inert material, which is just the ground up quartz. And so these are the materials that are not pozzolanic and would not yield any of those additional benefits that we get from pozzolans, like additional calcium silica hydrate or calcium silica aluminate hydrate, and all of those things that add durability to the concrete. This, then you can see we run strength activity index and report the percentages relative to the control, which is 100% cement, and all of these other ones have 20% replacement of cement with that SCM, in this case, pure base SCM, and we want those generally to be, according to the standard, higher than 75%. We look for 80%, generally keep an eye on 7-day and 28-day together, or look at the 90-day. Either one of them pass, it is a very good indicator we're not getting a filler effect or false positive, and that the material is good and reactive. We also keep an eye on water demand and making sure that all of those capillary pores that want to suck water from the concrete, we fill them up, and the material is happy, the amount of the water that it has received, and that we can incorporate it into concrete. Foam index is something that, okay, so then we finished that first round of the screening, and then everything checks out, then now we are scaling up already from about a bucket or a couple of buckets of the materials. So we are working with the supplier at this point to scale up with them, and we're trial matching concrete at this point. So for the materials that are a little maybe higher in carbon content or organic matter, we want to look at compatibility with air entraining admixtures for freeze-thaw durability. Well, we'll look at a full range of fresh properties, hardened properties, and also some indicators for durability. Drying shrinkage is really important for us in pavement applications, so we always keep an eye on that. And surface or bulk resistivity testing is something that we've been using as a proxy for durability evaluation. It's not a direct evaluation method, but it's a proxy. So back to our example, case material here being pure base, we use a control. Here's our trial batching. This is our concrete mix design. We look at admixture demand here, incorporate a couple of water reducing admixtures, and that is one of our area of focus, water demand, admixture demand, while making sure durability and cement hydration are in check. So these trial batching really helps us narrow down and finalize our mixture formulation, and looking at some of those fresh properties and trying to match target slump, target air, while finalizing and verifying admixture demand. Then we look at a host of mechanical properties, and a lot of our work, as I mentioned, is for Caltrans. So we always keep an eye on and making sure that the material, if they want to be on the approved materials list, then that is where they want to be. They want to make sure that they meet the acceptance criteria for drying shrinkage for mechanical properties, aka specifically flexural strength for us in the pavement area, modulus of rupture. Apologize for acronyms. Modulus of rupture here. We're also keeping an eye on modulus of elasticity, not something that we're quite used to in the pavement field area, but it is important. So we're keeping an eye on that, and compressive strength, which we're all very used to seeing as a quality control measure for concrete. So again, everything checked out. So we are progressing. We're looking at some durability indicator. Blue is our case material here. This is the result of electrical resistivity, bulk electrical resistivity, showing very good resistivity against the flow of electricity, electric charge through the sample, generally indicating that the pores are isolated and are not connected so that current can't flow through. But again, it is highly impacted by the ions that are also come along with the material into the pore solution. So got to keep an eye on that. And then drying shrinkage, again, is one of those important factors that we keep an eye on. And specifically, Caltrans does have a acceptance criteria that need to be met on 28th day for drying shrinkage. So we keep an eye on that. And it's a very important criteria for pavement performance. Okay, so then let's say everything checked out at the laboratory scale. Then we work with the supplier to scale up and produce a super sack or one or two super sacks of the material, depending on whether the material is cement or an SCM. So they will need to prepare the super sacks and deliver them. We have a really good partner that Central Concrete, and they produce the concrete. So we work together as a coalition. We come together, put our heads together. How can we put the test material in the truck, batch it at the plant. We do full scale trial batches a few days before the actual construction. Again, focusing really on that water demand, admixture demand, getting all the kinks out. We don't want any surprises on the construction day, although it is not bad we are not afraid of failure. I should bring that up again. So then comes the construction day, and we build 3 slabs and really evaluate constructability. So let me give you an overview of our facility. This is an aerial view of UCPRC and Davis. And what I have highlighted in the middle, the series of what we call test cells are actually located over here. I should have marked that here with an arrow, but hopefully you can see my cursor. But this is where we have one set of test cells, and then we're planning to mirror those depending on demand up on the north side as well. And you can see the forms going up here for that. This is the control that we paved, and this is the test cell, the case study that we're discussing today. We have so far placed 4 test cells, and we've planned for another 4 upcoming soon. And we're hoping that we can keep the momentum going, and we're hoping that we are placing 4 test cell clusters at a time every quarter. So that's our plan, and we're hoping that this whole framework can be repeated across California, but then also across different regions of the United States and then internationally to get the climate effect and also the aggregate and local materials validated. So for each one of these tested slabs, we put a strong emphasis on mid-range and long-range monitoring. And in order to do that, as you can see, these trees are basically strain gauge trees, and they're blown up here, and they're relative humidity sensors and temperature sensor trees. And these beams that you can see over here, they're unrestrained drying shrinkage beams. And the goal of this is that we track drying shrinkage. As you can see, concrete slabs tend to curl upward as they dry more at the surface compared to the bottom. And this, because the slab wants to pull itself back down, and because the truck axles along the joints of the slab ultimately want to exacerbate cracking across the middle area of the slab. So we're trying to monitor all of that curling and warping that may be happening across the slab, and we're trying to monitor with these companion beams how much restraint from the weight of the slab and from the adjacent slabs influence that cracking and damage that may develop over time. So this large this large table is not really intended to go through every single value. I understand there's a lot of value in the table, but what it is intended to show is that we do quite a bit of trial batches. You can see this is the control trial batch. This is a couple of trial batches we did with pure base, full scale in the ready mix truck. And these are the ones that were batched on the construction day. So kind of going through, really focus on admixture demand and water demand and making sure that were prepared. These are photos from the construction day. We focus a lot on measuring the bleed water, measuring constructability, finishability. We verify the water and admixture, and then full-blown quality control testing for both fresh properties, mechanical properties, durability. So the goal of this, again, is full assessment and evaluation. And as we're doing this, we're addressing all of those risks with testing, stepwise testing. These are some of the results, outcomes for our case material here, and the results of all of the fresh properties that were measured. We also measure maturity. We measure setting time with respect to maturity, and that helps us then translate the setting time onto the slab. So here are the setting times inside the slab. And then we are trying to come up with a method to then cut the joints at a timely manner with respect to final set time, with respect to the cement hydration development, so we can minimize the amount of raveling that otherwise may develop across the joints as they're being cut, because this is one of the points of an area of water. And it could be one of the Achilles heels of concrete pavements along the joints if they're not cut in a timely manner. And then on the construction day, we also cast a series of specimens, and the goal of them is a full quality control and monitoring of mechanical properties and durability, and basically kind of seeing if everything conforms and checks with the previous steps of evaluation. Here are a couple of just examples of some of the results that are coming out now. For the first test cell, our case study here, compressive strength is showing the progression of compressive strength. Cell 3 is our test material. Cell 1 is the control. And so the measurement of all the strength coming in with time and progressing. This is electrical resistivity measured on companion specimens that were cast for both of those two test cells. And again, we see a good progression. And so as we review these test results, we want to think about that framework and how it was a feedback loop. So if we identify some areas that potentially we see improvement possible, that we want to be able to go back a step, or if not, go forward a step toward agency deployment in pilot projects. Some of the additional materials that we have in the pipeline coming up for Lab2Slab evaluation includes optimized concrete mixtures with supplemental fines, and this can include rock dust from aggregate production. So these are industrial byproducts that we have quite a bit of abundancy and have very low reuse or recyclability. These are baghouse fines that are being collected as part of asphalt production as the aggregate is being heated. Other resources that we have abundantly available, primarily in the western area of the United States, include diatomaceous earth, ground glass pozzolan that we're working with a supplier here, wood ash, all kinds of biomass ashes, in fact, particularly important for California. Wood ashes, almond shell ashes, almond hull ashes, excuse me, as well as rice straw ash is something that also we've been working on recently. Biochar is something that has come up quite a bit, and we're looking at those for incorporation in concrete, as well as alkali activated concrete, as they represent an alternative to using Portland cement for producing concrete. So as we're going through that step, and I showcased how we've implemented one material, one pozzolan so far, in this presentation, I want to highlight and point out that communication strategy is also key to the success of overcoming and bridging the valleys that we talked about. And so just some photos from the event. Every time we do these constructions, we'd like to invite a stakeholder, broad range of stakeholders, and we think this provides a really good opportunity for everyone to informally network, but also exchange, observations and just see how the material is placed firsthand. We also like to partner with conferences for formal exchange of information. This is the top is a picture of the California Concrete Pavement Conference that was held in April. We're hoping to have that annually here at Davis, and then have that together with demonstrations, slab demonstrations, and again help get that information out and help with really cross-pollination across agencies, industry, implementers, contractors, as well as academia. And then training is a huge part of this, and we have learned lessons from some recent implementation of some of the cementitious materials. We've learned that training of the workforce is part of this, is a key part of this, and we want to make sure we want to play a critical role in this. The framework and those valleys cannot be bridged without proper training of the workforce that actually puts the materials down and to implement it, and also the designers and the specifiers that would specify the material in their mixes. Reporting is also very, very critical. We want to make sure to have at least annual reports that report and communicate the construction and the test results, if not more frequent, and then continually to provide support, the performance data, the language for either modification of specifications or drafting new specifications if needed. And I have a few examples of some of our recent reports. This report, Lab2Slab2Practice, is basically a full documentation of this presentation that I gave today. You can access the full report over at this address, and we're gonna share these slides with you so you can access the full report if you're interested. Here's another example report that focused on a comprehensive literature review that we did to identify various alternative supplementary cementitious materials could potentially be implemented within the concrete industry. Again, the address down below if you are interested. Here's another literature review and industry survey we lately did on fibers for concrete and for concrete pavement applications. And would hope to continue those reportings on a regular basis. So just to kind of wrap up and a recap of some of the major takeaways from the talk, what we discussed is that we need to accelerate the pace of change, but we also need to be open to change and to applying improvements. We got to overcome and bridge those valleys of death with performance data, with effective risk management frameworks, and with testing, stepwise testing, and helping the technology and the innovation to scale and to be adopted across the entire population. It is important that we check environmental claims, market acceptance, cost competitiveness, all of those at early TRLs, but also keep an eye on their progression as the material gets scaled up or the technology is scaled up. Proactive communication and strategy is key. Reporting is key. Sharing the data on the performance data is key. Developing standards and workforce training is key, and would hope that this type of risk evaluation framework then can be replicated across, various materials, various climates in the US and internationally, and to help accelerate the pace of change across our industry. It was a pleasure giving this talk. If you are interested, feel free to read more on our website, reach out to me. And now I'm happy to take any questions or comments that may be there.
Thank you so much, Somaya. So there is a question in the Q&A box. I don't know if you're able to see it. Pull that up at the bottom of your screen. I'm also happy to say them for you, but sometimes it's helpful to see it written. And then if anyone else has any questions, please feel free to add them, ideally to the Q&A box, although it looks like we're also getting a few in the chat window.
Okay. So hi, Larry. Larry Rowland has asked a question about why do you prefer pozzolanic less reactive over hydraulic more reactive in the first round of the screening? So Good question. A lot of, the emphasis may be that, we're looking for the ones that are maybe a lot more pozzolanic reactive, but the idea here, or the point here I was trying to make, is that we're not necessarily looking for the ones that generate a lot of heat. We don't want to get in trouble with super reactive, highly heat generating materials, while we can still, get away with moderately reactive materials. Also, we don't want to put a lot of effort and a lot of energy into continually to grind the material finer or thermally activate the material even more to get more reactivity from them. So the point here is that if generally with moderate amount of energy and cost put into getting the reactivity that we're looking for, and if we're getting the type of durability we're looking for, and make that work, generally we think that is sufficient, rather than trying to get to a highly reactive material that generates a lot of heat. So that's where that was coming from.
Thanks.
You're welcome. And thank you for the question. Okay, so there is a question from Mihoyo. Hello, good to see you again. And the question is about diatomaceous earth and whether they're available in California, or whether they're suitable, the ones that are in California are suitable. This is a question that we get actually quite commonly when we present diatomaceous earth. It does, trigger interest from the audience. It is a material that is actually available. I don't have the slide firsthand, but I can definitely add that to the slide deck when Kelsey shares them. But we do have the report of it, of how much is available. Quite a bit of it is available. A lot of it is going toward the filtration industry, brewing industry, for pools, filter applications, right? And lightweight application. We are working with a supplier on looking at their reactivity. They are amorphous silica, is what they are basically. We call them like dead tiny animals that have been, pile up at the bottom of lakes and the seas. And the only thing with them is that you got to keep an eye on potentially their water demand, and they do need to be, particularly developed for SCM and concrete application, because we also looked at the ones that are on the market for filter application, and those are generally very, very high demand. So our early on testing, the initial round of testing for reactivity, shows that they are in fact pozzolans. Their water demand can be controlled. It is manageable. Our research shows a little bit of thermal activation is very helpful, in fact, but at low and moderate temperatures. We don't need super high temperatures with them. So we think there's quite a bit of potential. So in fact, we just recently had a meeting with the supplier, and they're interested also to continuing and pursuing more, and hopefully we'll see more on that. Okay, so a question from Quan Zhang, another old friend. As a faculty member, it seems we are in between agency and contractors to support. What do you think the role of researchers in the university to promote the new technology adoption? And yeah, that is a really good question. A lot of times, not to beat down on faculties, that is not the point here, but what I'm trying to say is that a lot of times we come across really great ideas, light bulbs, and we publish papers on it, and the getting it all the way to the full arc and getting it all the way to implementation, it seems like a huge mountain to overcome. So really the point of the framework is to lay it out in front of us that, look, for a material, for a technology, for research to become a daily practice, it takes time, it takes effort, and it has to go through this entire loop. And this is what it looks like. So I think from our point of view, just having this arc in front of us and to look at it and being able to identify the process, and this is not just for academia, this is also for innovators, for producers, and for agencies to be aware of it and play their part in various aspects of this. And for us to come together to make that arc happen is essential. And as we go through this and build coalitions, we should be able to pull this off as a sector. Hopefully I answered your question. Be happy to chat more. So that was Q&A that I looked at.
Yeah, I actually have a question to tack on to that for you. I know we have a number of materials companies, both here in attendance today and as members of the Materials Decarbonization Sustainability Center. So kind of with them in mind, I was curious if you could address like what you think are the key steps for new materials companies to take in terms of like what priorities they should have to de-risk their products and get them adopted.
Yeah, I think a lot of this presentation was kind of geared toward, all of the early innovators, right? Because I come across a lot of material either owners, they're a permit holder or they're a landowner or they're already in the production industry. So the question is, what do I need to do first? And we thought having this a stepwise approach was helpful so they can see what it takes to get a material tested and evaluated and get it all the way to implementation. And I've seen, we have a broad range here on the call that I've gone through, and there are various scales, the various stages of that. We could call it TRL or steps, or so starting off with that small scale testing and scaling up, but then continuing to have an eye on. We know a lot of the barriers and challenges are some of the larger ones that need to be overcome, whether permitting is an issue or not, right? And in California, that's one of the big ones that might not be as big in other areas of the country. But funding for scaling up, going from bench production all the way to factory scale, those are the big ticket items. What we've noticed is that, and this kind of goes back to Quinn's question, is that what we can do, at least in academia, helping out, or industry and consulting firms, is provide performance data. So the more validation that suppliers can gather, and the more performance data that they can generate and put it in front of the funding agencies and capital ventures, or that helps because it addresses some of those risks. So the risks continues to go back across all of the stakeholders, and it includes funding agencies because they also want to know, well, if I fund a factory, is there a demand for this material? Does this material work? Is this going to be a failure on me, right? And then it goes back on and on. Are they going to be able to take that risk on?
Thanks so much for the presentation, Samaya. I wanted to add on to some of the questions that you've already answered. We've heard from several groups that are interested in alternative materials that there are kind of some unique constructability issues. And I know that you mentioned setting time as well as a couple of other parameters, but have you been able to integrate any additional constructability measures while you're doing the slab testing to see effectively how this might change in an in-practice situation? And how are you effectively getting that information back to the groups who can modify the materials as well as the groups who might be interested in using the materials?
Yeah, so that is, in fact, yeah, you're right. It is one of the nuances of working with, various materials now that are different than cold fly ash, right? Because they're cold fly ash and, it's just a spheres and it's easy to work with. And now everything kind of gets compared to cold fly ash. You want to understand, what are the impacts of that in terms of fresh properties, constructability. So some of the things that we've worked on right now, my team is working on an absorption test, and we are kind of applying some kind of a water drip, applying water, drips of water, drops of water, and bringing the material kind of to a saturated surface dry, and then we're using thermogravimetric analysis to identify available water or free water versus water that is trapped inside the tiny nanopores that don't want to come out. So we're kind of combining a very practical approach that's applied to sand with a mini cone, and then we're combining that with an analytical method to see if we can kind of identify, how much water demand are we really talking about here? Is that an issue for this material? Is not an issue? And we're really focusing on practical aspect of it, but also small scale, not seeing a test that can be run easily. So that's one of the tests. The other test that I was introduced to, I think it was by the Federal Highway Administration. It was the Jagan's group, the mobile trailer. testing facility, and we cast very small slabs, and then you apply holes in the fresh concrete, and then you run the trowel over them, and you count the number of runs that it takes for the trowel, to fill the holes, and you look at the finishability. There are other performance tests that have been developed by other groups, like the box test, and kind of look at the edge, and see if you have honeycombing. And then another thing that we're doing lately is verify the water content in the mix by using very, very high temperatures. We're applying some of our furnaces and some of our ignition ovens to verify the water content right on the dot. And if any corrections are needed, then that enables us to, within 10 minutes, having the water that was in the truck, the water that was in the drum. So we are keeping an eye on a lot of those. And then, I would say one more thing, isothermal calorimetry, just looking at hydration of the cement. And again, that's a tiny, tiny sample that goes in, but it just tells us so much. And we look at how the water content and the admixture affects the hydration of the cement. So we kind of run all of those on tiny, tiny samples, and keep an eye and pull the levers up and down on water and admixture and come up with those values that you see in trial batches. We hope to write all of this in some sort of a report and have it out soon.